Hi. In this video, we're going to go over exponential growth and decay, a pretty interesting and important topic in understanding how exponential functions work. And so we know exponential functions are functions where we have a base, which we raise to a power. For example, we could have 2 to the x, or 3 to the x. We can also have a base raised to a power that we multiply by a constant factor. For example, we could have 3 times 1/2 to the x, or 4 times 6 to the x, right? Where this 4 and this 3 aren't being raised to an exponential power, but nonetheless still have an impact on our overall total function, right? So in this case, these would be our growth rates, right? So, and today we'll talk about the meaning of those growth rates and how they translate into exponential growth and decay. I think the best way to do this is by going from tables of values to equations to graphs to really see the relationship and see why we call certain things exponential growth and why we call certain things exponential decay. So let's say I'm in a laboratory and I have with me a petri dish of bacteria. And I notice a pretty interesting phenomenon, right? So I start my day, spending 0 time, and I notice that there are, let's say, 10 million bacteria in that dish. I come back and I check after 1 hour, and now there are 20 million. I come back after 2 hours, and now there were 40 million. I come back after 3 hours, and there were 80 million. And I quickly look and I say, hey, this looks like an exponential relationship, right? Each time I come back after an hour, they're doubling in size. So I say, I might want to model this. It sounds like an important thing to do. So I say y equals, what does y equal? Well, it looks like 2 to the x, that all my values are multiplied by 10. So 10 times 2 to the x, right? Because this 10 isn't being raised to that power 2. I'm not doing 10 times 1, and then 10 times 2, and then 10 times 3, right? It's 10 times 2 to the x. So 10 times 0 is 1, that's just 10. 2 to the 1, that's 2, times 10 is 20. 2 to the 2 is 4, times 10 is 40, and so on and so forth, right? Now to actually graph this. Right, so I start out at 10. Actually, let me space them out a little bit more so it's easier to read. Okay, so I start out at 10, then I go to 20, then I go to 40, then I go to 80, and so it looks pretty dramatically like an exponential curve. And of course, if I were to go back in time, I'd have less and less bacteria, but I wouldn't have 0, because it's impossible to get 0 out of this function, right? I can't solve this, right? I can do 2 to the negative 1 million as my x. That will still just be 1 over 2 to the 1 million, which, although very small, this is a very small number, it's not 0. So we can't have that. So this can never touch the x-axis. The y value can never be 0. And now this is what we call an exponential growth function, right? It's growing, it's getting more positive, we're having more bacteria overall at a exponential rate, right? So when your function is increasing, its y values are getting greater and greater, you have exponential growth. But let's say while I'm doing my laboratory activities, I accidentally get clumsy and I knock in, a canister of bleach or some other toxic material into my petri dish. And the bacteria don't like that. And they start dying off pretty fast. And now, I know that an hour before I did this, so let's say at -1, there were say 12,000 bacteria, right? When I first noticed it, and I immediately measured afterwards, there were 6,000 bacteria. Then an hour afterwards, I measured again, and there were 3,000 bacteria. Then 2 hours afterwards, I came back and measured, and there were 3/2 million bacteria. I say, oh no, this looks really, really bad. This actually looks like they're getting smaller and smaller exponentially, right? This is, by times 1/2, and this is, a half smaller, and this is 1/2 of this as well. So I say, I need to model this. So I know I have, 1/2 as my rate, right? So I'm going to have something times 1/2 to the x. In this case, I notice, hey, that's probably going to be 6, right? Because 6 times at 0, right, when this is just 1, this is 6. And that's how I know what my constant is going to be. Whenever my x value is 0, my y value is going to be that constant outside of my rate, right? And my rate is, of course, how smaller or bigger I was getting, right? So in this, I was getting 2 times bigger, so I knew my rate, what I raised into the x would be 2. In this case, I'm getting a half smaller, so I knew that my rate's going to be 1/2. So I have 6 times 1/2 to the x. What does this look like? Well, I know my position. Actually, I'm going to do it on a separate graph just so it's easier. My, let's say, right, I'm at here, then I go to 1, and I'm at 3. Then I go to 2, I'm at 3/2. So it looks like a pretty severe decrease. And of course, if I would go to -1, I was at 12, right? So it looks a lot like I go on this. And then of course, if I can go further and I say, okay, let's say 3, right? Well, that's 6 times 1/2 to the 3, which is 1/8. That's 6/8 or 3/4, which is less than 1. So it's looking like this. And of course, we get closer and closer to 0 as we go on. But of course, we can't reach 0 for reasons we already discussed. And this is what we call exponential decay, where as our x values increase, our y values actually decrease. We keep getting smaller and smaller and smaller until we're getting bigger and bigger and bigger. Right? In this example, as our x values were increasing, our y values were increasing too. We were curving upwards, right? But here, as our x values are increasing, our y values are decreasing. We're curving downwards. But notice that these curves are the same. Like one of these, goes upwards and upwards and upwards and go down to infinity. This one goes down and then kind of lessens off because it can't reach 0, right? We're getting half smaller, and once you get down to it, right, like 1/2 of 1/1,000,000th is going to be really, really, really small. So you're not going to see these, steadily bigger and bigger jumps upwards, right? We're going to see smaller and smaller jumps downwards. And that's the difference between exponential growth, right here, and exponential decay, right here. So when a problem asks you to say, is this equation or is this relationship exponential growth and decay, you can look at their graphs and say, does that match the pattern of growth or decay? You can look at their equations, right? If I have a 2 to the x or 10 to the x, right, that's a number greater than 1. That means that I'm going to keep growing, right? Every time I increase my x value by 1, I'm getting 2 times as big, or this was 3 times as big. If it's less than 1, that means I'm getting smaller, right? If this was 1/2, I'm getting half as big each time I go down. Or if this was 1/3, I'd be getting 1/3 as big each time I go down. And that's the difference between exponential growth and exponential decay. I hope you found this helpful, and I hope you have a great day.